Good evening. Welcome to the second talk of Heisenberg Colloquium series on quantum materials and devices. Today's speaker is Professor Sandvik from Boston University. Most of you know him, but still, as a formality, I'll do that. Professor Sandvik is one of the most celebrated quantum matter theorists at Department of Physics, Boston University, USA. He completed his PhD from University of California, Santa Barbara in 1993 and joined Boston University in 2004 as an associate professor. He has a major contribution in the field of strongly correlated quantum many-body theory, and his famous contribution is development of the stochastic series expansion, quantum Monte Carlo. And this SAC is one of the most widely used numerical method for correlated system and for bosonic system as well, and has immensely contributed in the field of magnetism also. And he received many prestigious awards, including the Borite Second Science Prize in 2001. He is also fellow of American Society and in theoretical physics. With this, I'll request Dr. Sandvik to present. Thank you very much.
Well, thank you very much.
Just one quick request. If there are two devices in the same room connected to this meeting, maybe one should switch off its audio because I'm getting a big echo, perhaps because there are.
So I hope it's not my device because I have two, but I have the second one turned microphone off, so I think it's not. It's not me. I hope.
Yeah, now it's fine.
Actually, it's fine now.
Okay. Well, thanks a lot for the introduction and thanks for having me. It's a great pleasure to appear in Kolkata. Actually, I was in Kolkata in February 2020, just before the pandemic hit. So I have fond memories of the life before, which seems so distant now, but hopefully it will be back to normal soon again. So today I will talk about work on the deconfined critical points. I will try to explain what that is and why it is enigmatic, as I say here in my title. So I have many collaborators in this work. I will not read all the names, but you can see them here. What I'm going to talk about is a combination of numerical work, some contributions from field theorists, as well as some experiments that I was participating in, or at least discussing when I was spending some time at the Institute of Physics in Beijing, also before the pandemic. Okay, so unfortunately I cannot use the presenter mode in Keynote. We just tried it and it doesn't update, so I will just have to show it in this mode, one slide at a time, unfortunately, but hopefully that's okay. So the context of this work is quantum magnetism. So I'm giving a very sort of basic, short introduction. So imagine that you have two spins and they are coupled in this way, which we call the Heisenberg Interaction. And I want antiferromagnetism, so J is larger than 0. So then if you just think classically, now it looks a bit funny because this is an animation. It's supposed to be two anti-parallel spins, but then they can be oriented globally in any direction because we have this O3 symmetry. So that's the lowest energy state classically. But if you look quantum mechanically at spin 1/2, then of course the ground state is a singlet, and there's a gap to triplets. So that looks very different from the classical ground state. And we could go on, look at 3 spins. This is the classical Heisenberg model ground state. Again, you can do global rotations, but there's this 120-degree relative orientation of the spins. But this is the quantum ground state. So again, it's often convenient to describe ground states of quantum magnets with spin 1/2 in particular using singlets. And in this case, we also need an unpaired spin because we have an odd number of spins. So now the question, and I think this is basically, a summary of what the whole field of quantum magnetism is about. What happens when we, couple a macroscopic number of spins? And in particular, today I'm talking only about spin 1/2. And of course, that depends on the lattice we put them on, the type of interactions we have, the range of the couplings, and so on. And the point is that we can get a lot of different types of quantum many-body states. So today I will talk about ground state. So you should always think of the temperature as zero when we talk about the quantum systems. And what's very interesting is, okay, we have these states that in some cases retain some aspect of this singlet formation, but in some cases we also have states like I show here, the Néel state, which is very similar to a classical Néel state, but there are fluctuations. So we can have phase transitions between ground states in a way similar to what we have in classical stat mech when we look at phase transitions as a function of the temperature. Now instead we can look at some parameter g. So we could start from the Heisenberg model, which even with spin 1/2 has this classical looking Néel ground state with the global rotational symmetry and everything. But of course there are fluctuations. So this is just an idealized classical pictures, but in reality these spins fluctuate. But then we add some other interaction, and then we can have either continuous or first order transitions as a function of this parameter g. Okay, so that's basically what the field is about. So there's a strong experimental component, of course, in this field as well, which is motivating what we are doing. So I mentioned just one material here, which will come up later in the latter part of the talk as well. Strontium copper borite. It consists of layers, like this, and you see that these blue ones are copper sites, and they carry spin 1/2. They have unpaired spin 1/2s. And you can deform if you just keep these coppers and you look at how they're coupled. So there's a coupling inside, these dimers, between the spins in a dimer, and also between dimers. So basically this you should think of as a dimer. And I can deform that lattice into a square lattice where the dimers, copper dimers, are these red ones here, which have a coupling J prime. And then the dimers are coupled to each other in this way. With these couplings that I call J without the prime. Okay, so this one of course also has a red coupling, but I didn't show it. Okay, so it turns out this is a famous model constructed by Shasta and Sunderland already in the 1980s, and they found that this model has an exact ground state for some range of J and J over J prime. So basically there's a region where the ground state has singlets exactly on these red bonds. But then there are other phases as well, which I will mention later, other types of ground states. And the interesting thing is that this material can realize, if you put it under pressure in this material, the couplings that are about this in ambient pressure will change and will actually closely resemble what's going on in this material if you in this model where you change J prime over J. And the kind of phenomenon you could see there, we believe, is related to deconfined criticality, which is the topic of my talk today. So deconfined criticality is the kind of criticality that you have, or that you are, it has been suggested that you have if you can tune a model between the Néel state and what we call a valence bond solid, in this case a columnar valence bond solid, where you form singlets in columns like this. And this is a spontaneously formed pattern. So there are 4 equivalent patterns. You can rotate and shift these patterns to have 4 different ones that are symmetry related. So that's an unusual phase transition between the ground states. And for example, the excitations have some aspect of fractionalization, so that the excitations at the critical point are supposed to be spin-ons instead of magnons and so on. So I will talk about that, but to sort of introduce this topic of fractionalization and spin-ons, I will also just do one slide on a simpler one-dimensional system, and then I will talk about 2-dimensional models in which we can look at this phenomenon using large-scale simulations and get reliable results. And then towards the end, I will talk about a potential experimental realization in this material that I already introduced. And by the way, feel free to ask questions during the talk as well, not just at the end. So let's look at this famous one-dimensional example, which has a strong Indian connection because it was first studied by Majumdar and Ghosh. To be honest, I don't know where they were active in what university and so on, but in the 1960s they showed that this chain, Heisenberg chain with nearest and next nearest neighbor couplings as shown here, that it has an exact ground state if this ratio of couplings is 0.5. So then the ground states are dimerized. So there are, you can write them in real space like this, dimer products of dimers on alternating bonds. So that's an exact state, but away from that point, you cannot solve it exactly, but they did numerical work. This may have been one of the first numerical works on quantum spin models. And later people have done much more work, and this is very well understood now. So basically the Heisenberg chain by itself, without the J2 couplings, is a critical state. It doesn't have long-range order, so it has these critical correlation functions. And then this state, which we can call a valence bond solid, is the kind of ground state you have after a critical value of G, which is about 0.24. So if you go all the way to 0.5, you get this state without fluctuations in the singlets. And at other points, the system has a lot of fluctuations, and it's a phase transition similar to a Kosterlitz-Thouless transition between them. Now, what I in particular wanted to discuss here was the excitations of this chain. So if we just look at the Heisenberg chain even, but we mimic it as an Ising chain. So we just imagine that, okay, you have some long-range ordered antiferromagnetic state, and then you flip one spin, as you could do, for example, in neutron scattering. So you flip this one spin here, then you see you have two bonds where you don't minimize the energy anymore. And then those defects can separate without any additional energy cost. And that can happen spontaneously because of quantum fluctuations that is not included in this cartoon picture here. So you may wonder, why should this apply to this model, which is not an Ising model at all? And it turns out that it pictorially it does apply. Of course, you have a critical phase, critical state instead of long range ordered. And these defects are, extended in space. In fact, they are extremely extended in space. But still, one can think of them as independently propagating particles. So they have their own momenta, and that means that the energy for a given total momentum can span the whole band. So these bands are shown here with the dashed line. That's the upper bound for a given Q, and these arches here are the lower bounds. And this figure is from an experiment on this quite well-known, well-studied material. So one can actually see this spin-on continuum here. The spectral weight is very concentrated at the lower edge, but you can see that you also do see elevated scattering cross-section inside this whole area. So those are spin-ons, fractionalized excitations. So you can think of this spin one that was created was fractionalizing into these domain wall like features that carry spin 1/2. So this is something that people have been looking for in 2 dimensions as well, but clearly the pictures have to be different in 2 dimensions. So let me talk about non-magnetic states on the square lattice in 2 dimensions. So now I have in mind that we start with the Heisenberg model again and add something else that could give us some other states. So the Heisenberg model by itself again has this long-range Nell order. So we can basically get states of 2 different classes. We can get spin liquids or RVB states that have no traditional classical local order parameter. But then we can have a valence bond solid as well, as I already introduced. So the spin liquid, you can think of it roughly as some superposition of bonds where I say sometimes bond when I mean the singlet, pairs of spins in singlets. So these singlets sort of just fluctuate, and of course they can have a longer range. They don't have to be just between the nearest neighbors. Whereas the valence bond solid, you can think of as those singlets freezing into some pattern in a spontaneous way. So we don't want to break the symmetry of the square lattice by this G. We just want to do something that makes it form this order spontaneously. Or of course we may want to study spin liquids, which I will also mention later on. But today I will be mainly focused on the transition from the Néel state into this spontaneously formed valence bond solid. And again, that's according to theory beyond Landau-Ginzburg-Wilson type of phase transition, where in the standard scenario, if you have a direct transition into this from the Néel state, you have an order-to-order transition, and you would expect generically a first-order transition in that case. Now, this concept of deconfined criticality, I think, was coined in this paper here by Sentil et al. But there were many previous works that were sort of building up to this picture that they presented in this paper. And also here you can see, as you of course know already, almost all these works involve Indian scientists as well. So basically it's a field theory proposal, a field theory to describe what happens when you go from the antiferromagnet to the spontaneously formed valence bond solid. And I will not discuss the field theory. I'm not a field theorist, and in the audience we have many people who understand this very, very well. But the point is that there's a field theory proposal, and there were some calculations within that scenario. But it turns out to do calculations, it's very hard to do it for our normal SU2 spins. But if we go to SUn and take n large, then one can do what's called 1/n expansions, or you can just look at the n equals infinity point, which turns out to be something similar to mean field theory. And based on that proposal, they found that this transition should be continuous for large n. And then they were brave to conjecture that it should apply also down to n equals 2. So, maybe they were very brave, or maybe they were, encouraged by the fact that there were already some numerical results showing that this possibly could be a continuous transition for SU to 2 spin 1/2 spins. In any case, that caused a lot of excitement because, again, it's something involving the role of topological defects in this transition and so on, and the field theory itself is written down not in terms of order parameters, but in terms of these deconfined spin-on fields that you should have at the critical point. So, I and many other people were, very excited to try to do further work and with lattice models and see if we can confirm or clarify this scenario. And then the question is, what kind of models should we look at? So the traditional way, for a long time to look at, possible valence bond solid states like here was to introduce geometric frustration, or just, longer range competing antiferromagnetic interactions in the square lattice that, for a long time had been suspected that it could give rise to this kind of states. But it turns out that it's very hard to study such models using unbiased numerical techniques. So what we would like to do is to use quantum Monte Carlo simulations, where we can go to big lattices and really study criticality at the level that you are used to in classical Monte Carlo simulations. But it turns out we have this so-called sign problem for frustrated models, which basically if you don't know what it is, I can just say that it's a technical problem that makes it almost impossible to study certain models using this method. So instead, the path we took was to design models. So sometimes we call these designer models now. Design models that don't have sign problems but allow us to study this kind of transition. So let me quickly introduce what we call the JQ model. So the Heisenberg model is basically a sum of singlet projectors. So if you just subtract 1/4, or actually subtract 1/4 from your Hamiltonian, you can write everything in terms of these singlet projectors. Okay, the sign indicates that the Heisenberg model likes to have singlets on the interacting bonds, but of course there cannot be singlets on all bonds simultaneously, so then you get some complicated state, which, well, it's the antiferromagnet in the end. But we can construct interactions which are products of singlet projectors. And these are just some ways. So this is the normal Heisenberg interaction. This is a product of 2 singlet projectors on nearest neighbor bonds. This is 3 of them, and so on. And we sum them over all lattice locations and also all the rotations, so that we don't break any symmetry of the square lattice. And you can imagine that, especially if we have these interactions with many aligned projectors like that, and we put them with a negative sign in our Hamiltonian, then they would favor the formation of a valence bond solid. So intuitively that's pretty clear, but when you have just 2 projectors in this way and in the rotated way, it's not really obvious that you will get that. But it turns out in what we call the JQ2 model, which is just combining, the Heisenberg interaction and the one with the 2 singlet projectors, we do find this kind of phase transition. So, and there's no sign problem. If this sign here is negative, we don't have a sign problem, so we can study the model. So by now there are many variants of these models, and today I will just show some small subset of what has been done. But we can test predictions of quantum field theory with these models. We can also do things that were never done with the field theory. We can try to find new ground states, new RG fixed points, and hopefully if we do that, we can convince the theorists to look at them from the field theory perspective as well. And we can also make contact with experiments, as I will explain soon. Okay, so let me just quickly say something about the phase transition that we find in this JQ2 model. So again, I'm not discussing the technicalities of how we do simulations, but I just want to stress that we do finite lattices. There's no approximation beyond the statistical errors of the simulation. Okay, so to study the phase transition between these 2 kinds of states, we need to look at their order parameter. So the order parameter of the Nell state here is just the staggered magnetization. So we just add up the spins with these checkerboard pattern signs. And for the VBS order, we actually have dx and dy, because the VBS can orient with the dimers like this or like that. So in one case, we have dx order, and in the other case, we have dy order. And we can just measure the correlator on the nearest neighbor bonds, nearest neighbor sites, and add them up with appropriate signs corresponding to this columnar pattern. And then we can, from these order parameters, construct the bind accumulants, which are defined in this way. And they just are nice in the sense that if we choose these factors in the right way, then if we have an AFM phase, if we have that kind of phase, what we call US will go to 1, so that's the one based on the staggered magnetization, and UD will go to 0. And when I say go to here, I mean as the system size becomes larger and larger. And similarly, if we have a VBS order, then US will go to 0 and UD will go to 1. So this is shown here with actual simulation data. Well, now it's a bit bad because this was supposed to be an animation, so now I have to manually move this out of the way here. So this is showing you S and this is showing you D for different system sizes. And you can see that as the system size increases, I start to build up this step function feature here in both of them. But when one becomes close to 1, the other one becomes close to 0 and vice versa. And for big systems, there's only a small portion of this step just because the simulations are so expensive to do. It actually has taken many months to generate, especially the data for the biggest size here. So using data like this and many other quantities, we can do what's called finite size scaling. So we can, for example, look at how these crossing points of curves for different sizes approach a point, which is the critical point. So that's shown here. We look at different kinds of crossing points, and we can extrapolate the critical point. And we can analyze the slopes of these curves at the critical point as a function of system size. And in that way, we can extract critical exponent, RG scaling dimensions, if you will, and all sorts of things. And this has been done by many groups. Here I just list some of them, including Keda Damle and the collaborators who I think, who I know is in the audience. And also Arnab Sen has done a lot of work on this kind of model. So people agree broadly that this transition is continuous or possibly very weakly first order. So I will show some evidence today that maybe it's most likely weakly first order, but it's still a deconfined criticality, as you will see. So let me talk about the VBS order parameter a little bit more, because it's a very important it has a very important aspect for deconfined criticality. So again, we have yes, please.
Can I ask a quick question?
Absolutely.
Okay, now I can hear myself. I don't know why, but okay. So you said that the transition might be weakly first order, right? So then does it mean that it's not strictly deconfined, but only very weakly confined?
Yeah, so basically, I will come to that a bit later, but basically it means that if you think of spin-ons as particles, and then they will be bound if they will never fly completely apart at the transition if the transition is first order. So you can just think of it as very weakly bound spin-ons. But if the size of the bound state is several hundred lattice sites and the binding energy is super small, then for practical purposes it doesn't matter, and one can actually still see universal scaling and things like that. At least that's what we are arguing. So you will see a bit later on, and you can judge for yourself if you believe it. Anyway, so let me go to say a bit more about the VBS order parameter, which again has two components. So here I show something on a very small piece of the lattice, a 3 by 3 piece. So if we look up here first, you see here I have a y-oriented VBS. So in that case, dy is large and dx should be 0. If I measure dx on that kind of state, you should imagine that it's extended, but even in this small one, I guess dx would be 0. Whereas if the dimers are oriented like that, or shifted by one step, then dx is large, so that's why I put them here. But then the point is that in reality, these dimers have some very interesting type of fluctuations. So you can imagine that you fluctuate a pair of parallel dimers, and they can actually form what we call a plaquette singlet. So on a plaquette you actually have 2 singlet states, and you can write them as this one, horizontal plus vertical singlet orientation. Or you can do the antisymmetric version. So those are the 2 singlets you have. So if we talk about the plaquette state in the kind of models I'm discussing here, it should be the symmetric one. You may argue that has the lower energy. So anyway, there are fluctuations where basically the system doesn't look like a columnar order anymore. It looks more like a plaquette order. So if you repeat them, the next plaquette would be here, 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 and so on. And the plaquette states, they have both dx and dy. If you evaluate these order parameters in the plaquette state, you will find that they have both dx or dy, but one of them they can both be positive, or one of them can be negative, or both of them can be negative. So basically, these are just some special cases then, and then you can actually have any angle here, and that corresponds to some sort of fluctuation between columnar order parameters, or you could say that it corresponds to fluctuation between a plaquette state and a columnar state. So it's basically some state that has both types of order. And this we can also look at in our simulations. We can basically make a probability distribution of P of dx and dy. And then if we have a columnar state, we would basically expect to see only these columnar points here. So we would get a histogram like that. Whereas if we have a plaquette state, which, the squared order parameter that I showed you in the previous graph, it can actually not distinguish between plaquette and columnar. It can only say that there is some kind of dimer-based order. So if we have a plaquette state, we would see points like that. And since we have finite size, everything will be rounded here. There will be angular fluctuations and amplitude fluctuations, and these spots will have some shape. So let's see what we get. So already many years ago, we looked at that with the JQ3 model, which has a more robust VBS state. So we can actually go deep in the VBS state and really check if it's a columnar or plaquette type of distribution. And as you see in these graphs here, this is in the extreme case where we only have this Q3 interaction. We don't have any J at all. So J over Q3, which is often my parameter, will be 0. Then you see if my lattice size is 12 by 12, then you already see that you have these 4 points, but you also see that you have weight in between, which means that the system is actually fluctuating between those columnar states, and to be able to tunnel between them, it has to go through a state where it looks more like a plaquette state, where it would be somewhere here. But then when I make the system larger, these spots become smaller and smaller, and it's very hard for the system to tunnel between the 4 different states because there's not much weight in between. There's still a little bit weight in between. So there's still some probability of tunneling. And of course, this is all reflecting spontaneous symmetry breaking. So if you make the system bigger and bigger, even in the simulation, eventually it will be stuck in one of these blobs, and that's spontaneous symmetry breaking. But for any finite lattice, it will be able to tunnel between all of them. Okay, now let's look at the JQ2 model where the valence bond solid is not as robust. Then, the kind of ring-shaped distribution forms. So at first, this may seem very odd. What kind of state is that? Well, it's simply that these fluctuations that you see a little bit of here, to where the state can go into a plaquette state, so you can easily tunnel between the columnar state. This tunneling is, let's say, perfect here. It can go, between any plaquette state, any columnar state in a very symmetric way. And in fact, this was taken, early on as a confirmation of the DQCP scenario, because the prediction by Sentil et al. Was that the valence bond solid should have emergent U1 symmetry, which is this basically, in my naive sense of understanding it, it means exactly this, that the system doesn't distinguish between columnar or plaquette or anything else. It just has all these fluctuations in a U1 symmetric way. Now, when I go to a really big system, the ring doesn't look very perfect because it takes actually a long time for the simulation to cover everything. The simulation is sort of just slowly migrating here. But you see that the ring is getting thinner. So the amplitude of the order parameter gets less fluctuations, but it still has the angular fluctuations. If you look really carefully, you can see that there's some columnar feature here too, because the angular distribution is peaked at the angles, same as here. So now a very interesting aspect is that, this emergent U1 symmetry is governed by a length scale. So here I'm inside the valence bond solid state. And if I go to a really big lattice, eventually I would start to see these blobs here. Okay, in this case, I was so deep inside the VBS state that also already on L equals 12, I see the 4 blobs. But here I would have to go to a system size maybe 500 or something like that to see the 4 blobs. And the length scale governing that, meaning on what system size do those features appear, it's governed by an exponent which is larger than the correlation length exponent. So the normal correlation length, which you, for example, can associate with the spin correlations, has this form, divergent form as you approach the critical point, and this one actually grows even faster. Okay, and then it turns out that this second length scale may be important also to understand the spin on deconfinement and so on, and it's discussed in a paper, but I will not really have time to talk about that. So now let's go to the critical point. So, inside the VBS, we should expect eventually those 4 blobs. But yeah, as we go to the critical point, well, firstly, it should not look like a ring anymore because the ring is the amplitude of the order parameters. At the critical point, we should just get the maximum in the middle. So here for L equals 64, the critical point is around here. It gets slightly smaller if we increase the size. So here you sort of still see a little bit of ring feature, but here you don't. And this should be perfectly, U1 symmetric, perfectly rotationally symmetric. Okay, but now you may ask, I already showed that the JQ3 model had more of these, VBS features. I could go deeper in the VBS phase. You may ask what happens at the critical point if I do a JQN model and n is very large. And in a recent paper with my postdoc Jun Takahashi, we, as an example, studied a JQ6 model. So here, the interaction really looks a bit crazy because it's the Heisenberg model plus a 12-spin interaction, which is written as the product of 6 singlet projectors. And in that case, we see some histograms like this. So this is actually going through the phase transition, similar to what I show here, but we never see the U1 symmetric distribution. Instead, here you see one blob in the middle and some weaker features here. The blob in the middle actually means that this is on the antiferromagnetic side, which doesn't have any valence bond order normally, but here it already has a little bit of those features there. As you go through the critical point, you see that these 4 blobs corresponding to VBS order grow, and the blob in the middle just diminishes in weight, and eventually you just have the 4 blobs. Since Arnab Sen is in the audience, I should mention that he did something similar many years ago with another type of interaction where these singlet projectors were organized in a staircase fashion instead of in a column, and he presented very similar histograms for that. So this also means that in this JQ6 model, the transition is really a first order, because what this shows is that you have coexisting order parameters. Especially here, you can take this as coexistence of the 4 columnar states with the antiferromagnetic state, which doesn't have columnar any VBS orders. The blob is in the middle. So that's very different from the JQ2 model. So then you could also ask, well, if I do a JQN model, with smaller n, for what n does this first order feature arise? And this now addresses the question that Arnab asked before a little bit, if the transition is continuous or first order. So this is all unpublished stuff. It will appear hopefully, the paper will be written hopefully soon. So if we do the JQ4 model, then we can see, now I don't show the histograms. Instead, I show the long-range spin and dimer correlation. So we look at correlation functions at, sorry, I'm trying to make sure that you see what I'm showing here. We look at the correlation functions at the longest distance of the lattice, which is L divided by 2. If we have a first-order transition with coexisting order parameters, then we would detect that long-range order of both quantities, at infinite distance. And there are several graphs here, but I put some orange lines to maybe guide you what would eventually happen if we sit exactly at the transition. Then you can see that in this case, we have non-zero values for both correlation functions at infinite distance. So that means long-range order. So we have both spin and and dimer long-range order at the same time in the JQ4 model. So now in the JQ3 model, that also starts to appear, that feature also starts to appear when we go to very large system sizes. And also in the JQ2 model, but in the JQ2 model, it's a bit uncertain because actually one of them still seems to dip a little bit and one becomes clearly non-zero. So it may be because we're not exactly at the transition point, which was the point of showing several values here. You can see how one of them becomes non-zero and the other one dives if we are not exactly at the critical point. But most likely also this one is weakly first order.
And this quick question. So did you estimate the critical point using Binder crossing here? Or
yes, well, several different ways actually. Binder crossings and also we can look at what I do here, several values. And that actually agrees very well with the Binder crossings as well. So yeah, we can discuss maybe that more later if you like. Now let me talk about spin-ons and one important aspect here, which is Arnab's question before. If this JQ2 model happens to be weakly first order, is the whole concept of deconfined criticality dead or not? And I would strongly suggest it's not. So let me try to talk about the spin-ons. By the way, I don't know how much time I actually have. I guess I prepared for about 1 hour, so I hope that's fine, and I hope I can.
You still have more, 16 minutes, 17 minutes.
Okay, good. So, the spin-ons in the 2 dimensions are supposed to be not domain walls in the same sense as in 1D, but a kind of vortices where, the 4 different domains meet at one point, and then there's an unpaired spin at that point. And of course, there are fluctuations, and one can start to think about, again, some angle that rotates continuously as you go around the vortex core. And those have to be created in pairs, okay? And again, if the pair is super large, then it's almost like they propagate freely. But if the pair is very small, it's more like a spin one bound state. So you can think of it as not spin-ons anymore. It's just some bound state which has some internal structure, but you don't necessarily detect the internal structure. Now, this kind of spin-on pair, actually, Jun Takahashi was lucky in one of our projects during a simulation. He happened to catch spin-ons in the action. So he got from an actual simulation configuration, he was able to see something very similar to that. Now, what's going on here, which is like the confining string of spin-ons, is quite interesting because there are strong analogies to quark physics that we have exploited a little bit, but not. There's much more to do. So you should think of spin-ons as vortices, but if they're bound to each other, the vortex, it's like a double core vortex in some sense. Vortex anti-vortex pair. Okay, so this is where I think I can hopefully convince you that even a weak first order DQCP is actually contains spin-on physics. So in this paper we looked at the dynamic structure factor of a system going through a deconfined critical point. In this case, we actually used a slightly anisotropic model, which is not important for my point that I'm making here. So I will not comment further on the fact that there's a little delta here. So we can actually calculate the spin structure factor, which is the one that you would actually measure in neutron scattering that I showed you a 1D example of before. So we have to calculate correlation functions in imaginary time and analytically continue to real frequency and so on. So here's an example of that, through some on some lines through the Brillouin zone. So you see that we have this very broad continuum, similar to what we had saw in 1D. I mean, it looks even broader. And then there's a very well-defined lower bound for given Q of this dispersion. And we were playing out around with fitting here, and we found that this energy, omega of K, I should say here probably, fits very well the lower bound. And we can get an upper bound as well. So this basically follows from a picture of two spin-ons. So when the field theorists here got that information, they immediately realized that that's the dispersion of spin-ons in basically in Dirac fermions that you get from the square lattice if you put pi fluxes in all the plaquettes. So this is actually that theory at the mean field level. And you see that it agrees, I would say rather well. So the theory doesn't take into account interactions and so on. So you should not expect it to match completely. So I would say this shows. So if the transition actually is first order, that means that these pi 0 point, for example, the energy doesn't quite go to 0. So that's one of the Dirac cones, and it doesn't quite go to 0. There's a small gap there. But if that gap is very small, it should not really matter. Okay, so now in the remaining time, I will try to connect to experiments. So I already introduced this material and I introduced the model as well. So it has two couplings, and it has been known to have 3 different phases. So there's the exact dimer ground state by Shasta and Sunderland, and then their solution breaks down at some point. There's actually a level crossing with some other state, which now is known to be a plaquette singlet phase. So very similar to what I showed you before. But here, the plaquette singlet phase breaks a twofold symmetry, because the singlets can only form on the plaquettes which have no diagonal bond pair. So it's a Z2 symmetry breaking state. And then there's an L phase when J over J prime becomes large, which is very natural. If these red bonds are not there, it's just the Heisenberg model. Okay, so there are calculations for that, but the calculations are not completely definite because technical issues. This is one of those frustrated, difficult models. Now, the interesting thing is that in neutron scattering, if you put high pressure, you actually change the ratio J over J prime in some way that is not completely understood, but at least it seems like we can get these phases. So one of the works I was involved with when I was at the Institute of Physics in Beijing was to try to extract the phase diagram of this material at high pressure and low temperature. And there had been some works before indicating that this plaquette state exists, but the phase diagram was not known. There was also some indication that the antiferromagnetic state exists, but we believe that it was a different state and not where we expect it to be. So in this work, the heat capacity was measured down to, depending on the pressure, we could measure it down to about 1.5 Kelvin or slightly higher at higher pressures. And basically, the transition is seen as a sort of secondary peak in the specific heat as a function of temperature. Let me not go into details here, but in any case, we could also, by looking at the low temperature behavior, we could say, is it a gapless or gapped state? And in that way, we could propose that there's an antiferromagnetic phase here, a plaquette singlet phase here. And then there could be something like a deconfined critical point, as has been proposed as well by others in this white region. But that region we could simply not reach because of technical difficulties. So that's like a Murphy's law thing here, right? Well, I don't know if is it Murphy's law, but of course the most interesting region is the unreachable one. Okay, so now we want to do some modeling, and of course we can study the Shasta-Sunderland model as people have done, but it's really impossible to say definitely something about the phase transition and so on with those methods because it's so difficult. So we constructed a model which basically is the JQ model, but the Q terms only exist on every second plaquette. So to make the VBS state similar to what you have in the Shasta-Sunderland model. So now symmetry breaking and plaquette singlet formation corresponds to the system choosing, should it have singlets on those plaquettes or on those plaquettes, right? So that's the kind of symmetry breaking. So that's very similar to what happens in the Shasta-Sunderland model. So to get to some universal features, it should be okay to study this model. And in this model, we found a first order transition that's shown here. This is just something, locating the phase transition. But we have coexisting order parameters very similar to what I showed you in those other models, that both order parameters scale to non-zero values. But very interestingly, we found that if we look at those histograms again, but now we look at histograms in a slightly different way. Now we propose that, well, the antiferromagnetic order parameters and then get singlet order parameters. We can think of that.
Professor Sandvik, your voice is breaking.
Oh, I see. Sorry about that. Is it okay now? Can you hear me?
Yeah, it's okay now.
Okay, yes. Somehow it's cutting off. I don't know if it's me or some connection. Anyway, so we have this vector, and we can actually look at the distribution of one component of the antiferromagnetic order parameter and the plaquette order parameter. And then we can see as we go through the transition, exactly at the transition, it looks like a circular distribution. I just show a quarter of it here. And that, along with other things that I don't have time to talk about, actually demonstrates that there's an emergent O4 symmetry at the phase transition. So this is an example of something unusual that I don't think people have discussed before, that you can have emergent symmetry also at the first order transition. And what we believe is that maybe this is not really asymptotically an emergent symmetry, but the symmetry is manifested on very long length scales, which is surprising because the transition itself is very clearly first order. So we may have suspected to see, something like that instead, not exactly with 4 blobs because we have a different singlet state, but something like that. And in another model, in fact, we have seen SO5 as well. So now let me, and this is sort of soon summarizing everything. I have a couple of more slides, but this is an important point I want to make at the end here. So if we look at the original DQCP scenario, we thought of it as, okay, we go from VBS to AFM. We just change one parameter, and it's a generic quantum critical point. So that means it doesn't really matter what model we use. But if we do look at a model with 2 parameters, it should be something like this. So we should have a line of critical points. In that sense, it's generic because we don't have to fine tune to get here. But then, we can never exclude that there's some sort of tri-critical point and first order transitions as well. So this is the scenario people have had. Now, in these 2 papers, which I unfortunately cannot discuss in detail, in the first paper here, we actually started to argue that this scenario may not be correct for the kind of models we are looking at least. And in this second paper, which I will say a little bit more about, it became more clear. But our new scenario is, I think, quite something exciting like this, where actually this continuous line of deconfined critical points may be unstable and open a spin liquid phase, which terminates at a critical point. And then there's a line of first-order transitions, and those first-order transitions should be like the ones I showed in this model, and we can also look in other models where we have a higher symmetry on some large length scale. And the deconfined critical point here has just shrunk to a multi-critical point. And so, this multi-critical point, we believe, is the one that has asymptotically exact higher symmetry, and that symmetry is still influences the system quite far away from the critical point. So if we cross, here, we see that emergent symmetry, but if we cross here, we should see a spin liquid phase. And in fact, in this recent work here, we did find the spin liquid phase in the Shasta Sunderland model. So that's something where I can only summarize it very quickly. We looked at excitations of the Shasta Sunderland model in a way very similar to what people have done for a long time in this Mashundra-Ghosh chain and also in other 1D systems. Namely, you can look at excited state level crossing. So it turns out that in this system of the Mashundra-Ghosh chain, you have a level crossing of an excited singlet and triplet, and that goes very quickly towards the quantum critical point. So the quantum phase transition is in the ground state, but it affects the low-lying excitations in a way that there's a level crossing. Now, this has been done also together with Arnab Sen, also in the 2D JQ model, so we could see such level crossings in the JQ model. And with Ling Wang, we also looked at the 2D J1, J2 model. And in this thing, which I will not discuss in detail, just show the slide here, we showed that such level crossings occur in the Shasta Sunderland model as well. And we can extrapolate the crossing points, and we find that there are actually two sets of crossing points, and they extrapolate in a way that makes us believe that there's a spin liquid phase there. There's some very recent field theory work that also seems to support the fact that this the curve of continuous quantum critical points actually is unstable to spin liquid formation. And there's then, of course, a lot of questions, what kind of spin liquid is it and so on. So now experimentally, it will be very interesting to look more in this region. So, there was our paper, and then there was another paper in Nature where they saw the same transition into the PS state that we had. They have more points, much more resolution, but you see this line here, this bright feature corresponds to our points here, but they did not go to as high pressures. But very interestingly, we didn't see any secondary specific heat peak here. And their secondary peak here also seems to go away. So I think this could potentially mean that there's a spin liquid phase in this material, which, according to my calculations with Ling Wang, it should be, if it's described by the Shasta Sunderland model, there should be a spin liquid between those phases. So that will be very exciting to look at. There's another scenario where, because of 3D couplings, there's not a deconfined critical point, but some line of first-order transitions ending at maybe a triple point. But we don't really know for sure yet which one is actually happening here. Okay, so I think I'll just put up my summary slide. And again, it was all building up to what I think is this exciting new phase diagram that I didn't have time to talk so much about, but I hope at least I gave you some impression about deconfined criticality, and that it may be in some sense not exactly what was originally proposed, and that numerics has led to some maybe even more exciting proposals. Okay, so thanks a lot for your attention, and if there is time, I can of course take some questions.
Thank you. Now the floor is open for the questions. Professor Damle.
Hi, Anders. Thanks. That was really exciting.
Hi,
one question that you almost are sort of asking to be asked is there a sign-free model with SU2 symmetry which has this spin liquid phase?
Yeah, so that's a very good question, and I don't really know the answer. But my guess is, but that's really just my guess, is that maybe if we look at sign-free models, maybe we cannot even quite reach the deconfined critical point. We can maybe get super close to it, and maybe that point itself and the spin liquid is something that requires a sign problem. But why should that be, right?
Right.
It's not clear. So of course that's like one of the big questions in
Yes.
the field, right?
Okay, thank you.
Yeah.
Arnav?
Hi, Anders. So I have a similar question to Kedar, but maybe just on that. So, I mean, wouldn't you naively think that if you have a sign-free model, then you will just have like a U1 critical point and not like a Z2 spin liquid, which may be extended? So, that's
yes,
one question.
why do you say U1 critical point? Oh, okay.
I mean, yeah. So naively, if you're in 2 dimensions, right? So if you want to get a gap, if you want to get a spin liquid phase, then you have these Z2 kind of spin liquids, right? And usually they require frustrated interactions.
Right. So here they actually claim that the spin liquid is gapless. So, this work that I didn't have time to talk about in detail, that shows a gapless spin liquid. Yeah, I should have emphasized that. Yeah, and then of course, another important question is, people have proposed, just in the regular DQCP scenario as well, that maybe we can never reach the DQCP at all in 3 dimensions, in 2+1 dimensions. People have suggested these non-unitary conformal field theories to describe some transition that, in some sense is out in the imaginary, in the complex plane, or in some dimensions slightly less than 3 or something. And we just see if we are in 3 dimensions, in our lattice models, we only see near criticality because we are in some sense close to that unreachable critical point. So I don't know now if the people who advocate that scenario, if they would be able to reevaluate that if we have this different scenario. So basically, can that really be a critical point, or is it just a triple point which is which has coexistence of all those phases, but it's so close to criticality that again for practical purposes it looks like a deconfined critical point.
I see. Well, I have 2 more questions, but I don't know whether you will allow them. But
he's not protesting, at least.
Okay, good.
Yeah.
Right. So the question is regarding the system that you suggested that you might have a very weak kind of a first order transition in these JQ type models. So there is a confinement length here. So basically, there's an internal structure to this sort of spin-off, right?
So Arnav, your voice is cutting up to the extent that I can hear you a little bit, but the question was not very clear.
Is it better now?
Yeah. Can you decrease the volume of your computer? Probably that way.
Well, now the volume is at medium, and I don't know if it's any better.
Okay. So
anyway, if you just state your question, in a very compact way, I think I can still hear it.
Yeah. So basically, the question is that you were talking about this internal structure of these spin-on bound pairs, which are rather large in 2D, right? So in 1D, if you have structures like that, then one can sort of see this internal structure by mapping it to some kind of an oscillator problem, right?
Right. So it turns out
is there something similar in
Yeah, so in 1D, I think you're right in principle, but in 1D, the spin-ons, at least in these, the J1, J2 chain, and also we can do the JQ chain, the spin-ons are not bound in 1D. They're always, deconfined, because there's nothing to there's no confining string, right? Because the
No,
spin
that's correct. But you can just imagine like a ladder model, and then there is a confining potential that you can tune.
Yeah, you could do some other models that have confined. That's correct.
So, but my question was, in 2D, is it understood what kind of simple quantum problem this thing maps to? Probably.
Oh yeah, now I see your question. Yeah, so this is super interesting, right? Because I think what you are asking is that, okay, now we have one bound state, maybe like that, but could we even have many bound states, right?
Yeah.
So so that there's an analogy which again I want to explore, but I haven't done yet. But with the mesons, right? So there's two types of pions. I think they're called now I forget. But the two pions, and one is an excitation of this bound state of a quark anti-quark pair. I think one is called rho, and the other one I forget. So is it something like that here? That if we look at this, which we should be in the VBS state to look at, so it's not even really just deconfined criticality, but could we actually excite like a bigger spin on anti-spin on pair because of the VBS? This confining string, like you said, it's like there's some analogous quantum problem, but it's not so clear if this can just be described as a potential, maybe to some extent. I think that's something that definitely would be nice to explore.
Your voice is breaking.
Okay, sorry, nothing to do, but anyway, it would be nice to explore. That's the point.
Okay, great, thanks.
Any other question? No. So then I'll ask the last question, and I think it's a very simple question, probably. You're talking about this spin liquid and this Shastri Sunderland model in antiferromagnetic regime, when all the J1s and J2s are antiferromagnetic.
Right.
They do see some sort of topological spin liquid also. So are you talking about that?
Yeah, so in the J1, J2 model, we had also looked at that one. So in that case, I think it's still quite controversial what kind of spin liquid it is. So there was a paper. There have been several proposals of spin liquids in the J1, J2 model, but there was one, high-profile one by Leon Balents and his student, and they claim that it's a Z2 topologically gapped spin liquid. But nobody believes that it's gapped anymore. I think there was some mistake in their extrapolations or even in the DMRG calculation, I forget. But they claim that there was a big gap, and everybody else is seeing, gap-less spin liquids. Now, the topological aspects of those, I think people don't know as much about yet. So it's a very sort of open field what, gapless quantum spin liquids, what kind of such things there are. I mean, there are these U1 Dirac spin liquids, but for example, about topological entanglement, entropy, and things like that, I don't think people know as much.
Okay, thank you.
Yeah.
And with this, let's thank Professor Sandvik for excellent talk. And thank you very much for agreeing and giving this talk.
My pleasure. Thank you, everybody.
Thanks, Anders. Good to see you.
Bye-bye.
Thanks, Anders. Bye.
Nice to see my friends.
Bye.
Bye.
Bye-bye.